Hi, everybody. It's Professor Mitchell. So today we're starting a new chapter, Chapter 8 on confidence intervals. So we'll start with a brief introduction in 8.1 on point estimates, and then we'll just go right into section 8.2. So a point estimate is a single value that best describes the population of interest. The sample mean is a point estimate of the unknown population mean, and the sample proportion is a point estimate of the unknown population proportion. So in this chapter, we're going to use confidence intervals to estimate the unknown population mean and the unknown population proportion. So that will start with either a sample mean or a sample proportion. Point estimates are easy to calculate, but do not provide any information about their accuracy. An interval estimate provides additional information about variability. So here you see a chart that describes the different situations we're going to look at in this chapter. There are two types of confidence intervals that we'll look at. Confidence interval for the population mean, we'll look at that first. And then later we'll look at confidence intervals for population proportion. The calculation of the confidence interval for a population mean depends on whether your population standard deviation is known or unknown. So we'll start with the known case in the sigma known case in section 8.2. All right, so that's where we are right now. A confidence interval for the mean is an interval estimate around a sample mean that provides us with a range within which the true population mean is expected to lie. A confidence level is defined as the probability that the interval estimate will include the population parameter of interest. So the assumptions in this section are that the sample size is at least 30, and most importantly, that the population standard deviation sigma is known. So remember, we just talked in the last chapter about the formula for the standard error of the mean, which is called sigma sub x bar. So that's sigma divided by the square root of n. We'll be using that to calculate this confidence interval, where, of course, sigma is your population standard deviation and n is your sample size. The purpose of generating a confidence interval is to provide an estimate for the value of the population mean. The confidence interval for the mean has an upper confidence limit, which we'll call UCL sub x bar, and a lower confidence limit, LCL sub x bar. The limits describe the range in which we have some degree of confidence that the actual population mean lies. So the way to calculate these limits, you see right here, you start with your sample mean, x bar. To calculate your upper confidence limit, you add z sub alpha over 2 times the standard error of the mean. And we'll talk a lot more about z sub alpha over 2 here in a second. That's called the critical z-score. To calculate the lower confidence limit, you just subtract the same amount from the sample mean. So that would be x bar minus z sub alpha over 2 times the standard error of the mean. All right, so let's talk more about z sub alpha over 2. That's called the critical z-score. The variable alpha is known as the significance level. It represents the probability that any given confidence interval will not contain the true population mean. So for example, if alpha was 0.10, then z sub alpha over 2 would become z sub 0.05, which is 1.645. So this is the z-score that cuts off the top 5% of the area under the normal curve. So it's the value that encloses 90%. That's not exactly right the way they said that. Yeah, it's really the value that encloses the bottom 95%. If they said plus or minus 1.645, that would enclose the middle 90%, okay? And would leave 5% in each tail. Okay, so the picture explains it a lot better than this little blurb right here. So you see 0.05 in the upper tail and in the lower tail, which leaves 90% in the middle. The z-scores that cut off that middle 90% are plus and minus 1.645. Now, there are certain values of alpha that are most common. And so we will, in a little bit, I'll show you a chart that lists different values of z sub alpha over 2 for different significance levels. All right, so you can see the total area to the left of the right-hand boundary is that middle 90% plus the 5% in the lower tail, which is 0.95. And the total area to the left of the left-hand boundary is just 0.05. All right, so for example, if an airline wanted to estimate the number of tickets sold for a daily flight between Dallas and Denver, suppose a sample of 35 flights gives a sample mean of 145.5, and assume that the population standard deviation is 30.2. And we want to calculate a 90% confidence interval for the population mean. So first we'll find the standard error of the mean, which is sigma divided by the square root of n. 30.2 divided by the square root of 35 is about 5.105. And then, as we just talked about, z sub alpha over 2 for a 90% confidence interval is 1.645. So then our upper and lower limits, the upper limit would be x bar plus z sub alpha over 2 times the standard error, comes out to 145.5 plus 1.645 times 5.105 is about 153.9. And the lower limit, x bar minus z sub alpha over 2 times the standard error is 145.5 minus 1.645 times 5.105, which is about 137.1. So based on our sample mean of 145.5, we are 90% confident that the population mean number of tickets sold is between 137.1 and 153.9. The margin of error is the width of the confidence interval between a sample mean and either its upper limit or its lower limit. All right, which would be just this quantity here that we add and subtract from the sample mean in order to find the upper and lower limits. Okay, so that quantity right there is called the margin of error. Here's a picture of what that looks like. Here's your point estimate, in this case, x bar. When you add the margin of error, you get your upper confidence limit. And when you subtract the margin of error, you get your lower confidence limit. And of course, the distance from the lower to the upper confidence limit is the entire width of the interval. Increasing the sample size while keeping the confidence level constant will reduce the margin of error, resulting in a narrower or more precise confidence interval. All right, so whenever you can, you know, a larger sample size is better than a smaller sample size. Okay. All right, so again, we're 90% confident that the true mean is between 137.1 and 153.9. So what does that mean? It means that although the population mean may actually, may or may not actually be in that interval, close to 90% of a large number of sample means drawn from this population will produce confidence intervals that include that population's mean. An incorrect but common interpretation of a confidence interval is that there is a 90% probability that this interval contains the true population mean. And that's incorrect because the interval either does or does not contain the true mean. All right, so a probability like that for a single interval doesn't really make sense. All right, so here's a picture that kind of draws more on what we were just saying there. So what you see here are a bunch of different confidence intervals. Here is the true population mean. So let's say the first sample mean was here, and the second sample mean was there, and the third one was here. It looks like they drew about 7 of them. In 6 out of these 7 intervals, the interval contains the true population mean. So that's kind of the idea of what a confidence interval is supposed to do. The significance level, alpha, represents the probability that any given confidence interval will not contain the true population mean. The confidence level of an interval is the complement to the significance level. And that confidence interval gets wider as the confidence level increases. And my favorite sort of simple analogy to explain why that is, let's say it's toward the end of the semester and you're trying to guess what your grade is going to be in a class. You might say, I'm 80%, or yeah, let's say I'm 80% confident that I'm going to pass the class. So that's a pretty wide interval that goes from, a C minus all the way up to an A. On the other hand, you could say, wait a minute, I'm getting this backwards. All right, start over. I'm 99% confident I'm going to pass. All right, so that's a wide interval from C minus to A. All right. As you decrease that confidence level, your interval will get narrower. So I'm just doing it instead of okay, let's start over one more time. I'm 80% confident that I'm going to get a B plus in this class. All right, that's a very specific grade. And that goes from, let's say, 87 to 89. Okay. I'm 90% confident I'm going to get some kind of B, or let's say I'm going to get something between a B and an A minus. All right. So that interval is a little wider. There's a little more uncertainty. All the way down to I'm 99% confident I'm going to pass the class. So that's a very wide interval that goes from C minus all the way up to A. All right. Okay, so now let's look at a 95% confidence interval. 95 means that 1 minus alpha is 0.95, which means that alpha is 0.05. So we're going to divide that in 2 for the lower tail and the upper tail. That means the area in the lower tail will be 0.025. The area in the upper tail will be 0.025. And you can see from table A2, if you look at table A2, that the z-score that cuts off the bottom 0.025 proportion of area is negative 1.96. And the z-score that cuts off the bottom 0.975 is positive 1.96. All right, so you can get that right out of table A2. Z sub alpha over 2, which is 1.96, and technically they should say plus or minus, encloses 95% of the area under the curve with 2.5% in each tail. Okay, so here's the chart that I was referring to a little while ago. So these are the most common confidence levels you're going to run into as you do the homework. And also in real life, whenever you have to deal with a confidence interval. So 80%, 90%, 95, 98, 99. And then over here, you see the corresponding critical z-scores. So this chart would be a good thing to have You know, if you have 1 or 2 sheets of paper where you collect all your formulas, you might want to add this chart to that sheet of paper. So if you're doing an 80% confidence interval, your critical z-score is 1.28. We already talked about 90 and 95%. If you're doing a 98% confidence interval, your critical z-score is 2.33. And if you're doing 99% confidence interval, your critical z-score is 2.575. All right, so what about when your sample size is less than 30? Well, we talked, I believe, in the last chapter about there are 2 situations that will guarantee that your sampling distribution is normal. The first one is that your sample size is greater than 30, or the other way you know that your sampling distribution is normal is if the original distribution is normal. All right. So if your sample size is less than 30, then you need to know that your original population has a normal distribution. All right. If you don't have one of those 2 things, either your sample size is at least 30 or your original population is normal, then you can't use the methods in this section, basically. But we're going to talk about that maybe a little later in another section. With n less than 30, the central limit theorem cannot be applied, so we can't say the sampling distribution will be approximately normal, but the sampling distribution is always normal, regardless of the sample size, if your population is normally distributed. Okay, so if you're working with small samples, just look for something that says the original population is normally distributed. So for example, if a manager wanted to know the average time it takes to complete the required forms to hire a new worker, suppose a sample of size n equals 18 gives a sample mean of 1.28 hours, and we're assuming that sigma is 0.2 hours and that the population follows the normal distribution. And we want to calculate a 95% confidence interval for the population mean. All right, so first of all, we can use the methods of this section because even though we have small samples, we are told that the original population is normal. Okay, so first we will find the standard error of the mean, which is 0.2 divided by the square root of 18. That comes out to about 0.047. Z sub alpha over 2 for a 95% confidence interval, as we talked about earlier, is 1.96. So now we'll calculate the interval endpoints. Your upper limit is x bar plus your margin of error, which is 1.28 plus 1.96 times 0.047. That comes out to 1.372. And your lower limit is x bar minus your margin of error. So that's 1.28 minus 1.96 times 0.07, which comes out to 1.188. So based on our sample mean of 1.28, we are 95% confident that the population mean is between 1.188 and 1.372 hours. And that's going to do it for this section. So we'll see you next time for section 8.3, where we'll talk about what to do when the population standard deviation is unknown. See you next time.